Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We are seeing the subject called compiler design. In the previous episode of the same subject series, we have seen the lexical analyzer and the syntax analyzer. The lexical analyzer scans the source program characters by character. It transforms the program into a sequence of lexemes, or as we call them as tokens. So, lexeme is the name given for the exact lexical construct, whereas the token will be a description of the lexeme in a pairwise format, so that your parser will be able to understand what it is. And then we have seen that is what is going to be the role of the parser. The parser treats the sequence of tokens which are returned by the that is your lexical analyzer and try to map them into the pattern which is the specification of the source language. And the lexical analyzer is making use of the regular expressions, whereas the parser it is making use of the grammar for description of the syntax of the programming language. And the remaining phases of the compilation are here. So, we have the semantic analyzer, then followed by the intermediate code generator and the code optimizer. That is code optimization followed by the code generation. So, what the semantic analyzer does is, it is actually verifying mostly it is verifying the type of your that is the various variables. So, for example, if I am having an expression like A is equal to B mod C, mod is an operator which returns the remainder after division. So, which requires that both B and C must be of type integer. The syntax analyzer has no role in determining what is the type of B and what is the type of C, but it will say that this expression is a binary expression with the one binary operator, that is nothing but the mod operation, with the two operands B and C. So, it is as per the syntax of the programming language, but whereas when you look at the semantic of the language, we find that is going to have a problem, that is you can't evaluate B mod C provided B is floating point value or even C is a floating point value or even both. Another thing is, for example, if I am having an array declaration, we must know that there is the index of the array must not exceed the bound which is being provided by the declaration itself. So, that is going to be the array bounds exception and the type mismatches. So, these are the issues being taken care by your semantic analyzer. So, it will not transform the code. For example, it will do some kind of typecasting also. In the case of like A is equal to B plus C, if B is of a floating point number and C is of an integer, then B plus C is supposed to be converted into a floating point operation by transforming C into another data type called float. So, that we have both the operands of same type, and thus we will be able to carry out a floating point operation. So, that kind of automatic type conversion we will be always calling it as coercion will be carried out by the semantic analyzer, provided it is supported by the programming language. So, if the language supports coercion, it is the duty of the semantic analyzer to take care of those activities, so that you are that is you will be able to come out of the reporting it as errors. So, that is the role about your semantic analyzer. So, now we have the next phase of the compilation, which is called the intermediate code generation. So, first you should know that is what is the meaning of what is the need for the intermediate that is code generation. So, we have the source program, and what we expect is only the target program. The target program means the object code. So, if it is possible to transform directly your source program into its equivalent, that is object program, then it is good. But always it is not very easy to transform it into your its equivalent, that is object program. So, for example, if you have an expression like A plus B multiplied by C, so there is a need for looking into the priorities and associativities of various operators. Even if it is a plus b plus c, so we need to compute a plus b first, then the result of that will be added with c. But if you do it in the other way, that is b plus c and the result will be added with a, then it may not be the correct one because of the associativity of plus will be from left to right. And in the case of a plus b multiplied by c, we must carry out b multiplied by c first, and then only it should be added with a. But now if you are that is considering all these factors when you are transforming it into directly into the object version, the issue is like how we will be that is stacking the operands. That is, we need to remember huge amount of identifiers and operators before generating the code for a bit of that is operation maybe at the rightmost end of the expression. If we go for simplifying the that is expressions, then it will be easy for the generation of the object code first, that is the first point. So, for example, instead of a plus b multiplied by c, if I have some temporary variable t1 is equal to b multiplied by c and t2 is equal to a plus t1, then it is not required to remember any that is your priorities or associativities of operators. First point. The second point is, when you are having an operator on this operation like b plus c, the generation of the code will be very simple. Just you load b, add with c and store the result back into the temporary name, maybe it is t1 or t2. The code generation is easier. Another important factor that will be really an advantage for us when you go for intermediate languages, the number of registers required for us. So, if I am having very large expression with no intermediate split up, then we need to have very large number of registers to store the values of the operands, because whenever we find an operand is there in your register, the operation will be much faster. So, that is what we will try to keep the that is values of the various variables into the registers, but when the expression becomes too lengthier or too complex, then there is a need for having multiple more number of registers to store the that is values before carrying out the operation. But when it is transformed into intermediate language, we will be having very smaller expressions with the 2 operands and 1 operator at the most. So, what will be the advantage there is, we need to have only very little number of registers, so that the resource requirement will be less and even the code translation will be much easier for us. So, that is the reason why we go for intermediate representation rather than directly converting your high level language source program into its equivalent that is your object program. Here is the details. So, it is the converting the intermediate that is the source program that is which is having very complex instructions into simple instructions. So, that is the first one, and then we can find that it is the compiler which can construct one or more number of intermediate representation. So, which is like we have 3 address codes, and we have that is syntax trees, and we have that is your there is another one is called the postfix notation. So, these are all the varieties of intermediate languages. So, it is not required that we must exactly that is go by only one intermediate language. So, it is fully depending upon the language specification. So, but the most familiar kind of there is your intermediate language is the 3 address code. So, where it is of the form a is equal to b mod, so b operator followed by c, but it is not required that always the syntax must be or the instruction must be of this form. Sometimes we may have an that is operand, we may have one operand on the right hand side because of the operator is going to be an unary operator, and sometimes we will be having that is go to statements, conditional or unconditional. So, these are the various kinds of instructions that we cannot avoid, but the condition there is we need to have at most there is 2 number of operands on the other side, and there will be only one resulting computation, and the operation will be only one operation. We exclude the assignment, other than that there will be exactly one operation. So, that we will be calling this instruction as a 3 address statement. Sometimes we will use even a syntax tree for its representation. So, which will be the representing the expression without modifying the hierarchical structure and the priority and association. That is your natural way of representing an expression or even a statement will be called that is syntax tree. So, everything will be integrated within the syntax tree. Everything I mean, that is your the syntax specification and the semantic specification and your hierarchical, the priority, associativity, everything is inbuilt as far as any syntax tree is concerned. Sometimes even we go for postfix notation also, so that will also incorporate all kind of priorities and associativities. So stack based architectures will be really finding its advantages to have postfix, because any postfix expression can be evaluated provided we have a single stack. So we have a stack means we go for push operation as long as we have operands, and we will go for the computation when we have an operator. So that is what the simple way of evaluating expressions, whether it is conditional expression or arithmetic expression or logical, whatever it is, we need to have only a stack for the entire computation. So that is about the intermediate languages. The condition for intermediate language, like first is it should be easy to produce, that is the properties, and then it should be easy to translate into the target program. So we have two ends, one is the front end, another one is the back end. The front end produces the intermediate language and the back end consumes the intermediate language. The front end should be much easier, find very easy to translate the program into the intermediate language, and the back end should find it's very easy to translate the intermediate language into the source program. So then only we will be able to say that your intermediate language is an efficient, that is intermediate, that is language. So if you find both the job, that is like you are translating your source program into its equivalent, the intermediate language is difficult, and if you find that it is very difficult to transform your that is intermediate language into its equivalent object program, then there is no point in going for intermediate language. So intermediate languages, we should find it easy to come up with the intermediate language, and at the same time we should find it easy to come up with the object language from the intermediate language. So that is the purpose of your intermediate language. So here we have the specific instructions, like one familiar one is 3 address code, which consists of a sequence of assembly like instructions with the 3 operands per instruction, and each 3 address assignment instruction has at most one operator on the right hand side, but we do not include the assignment as an operation there, it is implicit. And most of the time when you are splitting your program into that is your high level language instructions into smaller instructions, it is required to introduce number of that is your temporary names. So that part is being done by your compiler. So your compiler generates temporary names to hold the values of the computer values which are computed by the 3 address statements, and sometimes even we may have very lesser number of instructions than the expected one. That is 3 address means exactly 3 addresses not necessarily be there. As I mentioned earlier, if it is going to be a in-array operation, or if it is going to be a unconditional branch kind of things, so in that case we will be having lesser number of operands than having exactly 3 number of operands. And 3 address code includes even conditional as well as that is your unconditional as well as simple conditional branching statements also. So in the case of simple conditional branching, so what do we have there is something like we will be having if a less than b, then go to c. This is what the syntax for any 3 address statement which is going to be a conditional branch. We have that is a expression, that is relational operation. If a less than b, a relational operator followed by b, then go to c. So a is an operand and b is another operand, then go to L is another operand, that is L is another operand. What is the operation is, if a less than b, go to is the operation. So less than, go to, that forms the operator, and a, b, c are the operands. So these are the varieties of 3 address statements available, which will be produced by the intermediate code generator as the intermediate language. I will continue the remaining phase after a short break. Welcome back. We have seen the intermediate code generator as a phase of your compilation, and the next is we have a phase called code optimization. So which is the one of the optional phase as far as any compiler is concerned. It is because of, if you are concerned more on the object code version rather than how optimal it is, then we need not spend too much of time in optimizing your code, because more the rigorous optimization we need, more the time we have to wait or we have to spend for transforming your code. So if you are concerned only about getting the right result rather than going for the optimized version, that is we are not bothered about the time it takes or the space it consumes, then we can skip this code optimization phase. But nowadays we are having a lot of optimizing compilers, so where we find this phase becomes a very important phase where we spend most of the time in optimizing the code. So it is not a very difficult issue there because compilation is a one time job and execution is as many times as we wanted to have the program. So once if you spend some amount of time in optimization, so we will be able to save lot of time and even the space when you go for the that is your actual execution of your code. So that is what we sometimes we will spend. The optimizing compilers will come and spend a lot of time in applying various transformations on your code, but the condition there is, so the object code version, that is your the optimized code should produce the same result as the result produced by the original code without an optimization, but it may take less time or even less space for its computation. So that is what your optimization phase is expected to do. So here we have a description. So code optimization is an optional phase that optimizes the 3 address code without changing the meaning, so that the object program runs faster and or takes less space. So that is very important here. So it is expected to be faster or expected to take lesser space or expected to do both, that is it is fast and taking less space. So it is not a rule that we must have all the conditions satisfied together. So even if you find the code is much faster than the original one, it will be considered as an optimization, or it takes lesser space for its your execution, then it is there is a optimization, and if it is taking lesser time and lesser space, then that is also considered as an there is optimization. So most of the time we have similar optimizations, they will be improving the running time of the target program without slowing down the compilation too much. So like simple optimization means they may not take too much of time, but if you go for rigorous optimization, that is very complex optimization, then the optimization itself is going to be a very time consuming process. So most of the optimizations that is techniques are that is undesirable problems, we find that they are consuming too much of time. So we will go for selective optimizations based on the program requirement and especially to some section of the code rather than the entire program, and it is going to be done by most of the time by optimizing compilers. And there are two kinds of optimizations. One is called the loop optimization and another one is called the that is your local that is optimization. So the optimization can even be that is machine dependent or even machine independent. See if you want to find out what is going to be the machine for which exactly we are producing the machine the object code, then we can extract certain features from the machine, and so those features can be that is utilized by the optimizer, so that you can find out that particular code is going to be optimized for the specific machine. And many of the optimizations are machine independent optimizations. So where we will be doing lot of optimization, but we do not mind about what is the architecture for which we are executing the code. So now what are the criteria to be expected or to be met by your compiler optimizations? The first one is the optimization must be the correct one, that should mean it should preserve the meaning of the compiled program. That means the IO relationship should not be changed, whether it is going to be the optimized program or the unoptimized program, the meaning of the program should not change. And another one is the optimization must improve the performance of many programs. So even if you find that one part of your optimization that is enhances the that is code by in terms of performance, if it is having a drastic effect on some other program, then it is not going to be advantageous, because the optimization we are getting from this program may be compromised by some other program. So the optimization should have a positive impact on all the related programs. So we will be calling it as the best optimization. And another thing is, this is what a very important factor to be remembered here. So just because of we wanted to have an optimization, we should not go for doing the compilation for hours. So you try to spend some tolerable amount of time for compilation, within which we compile, optimize and get the object code, but rather than going for spending too much of time on optimization itself. then the effort required for that is also very important. So, for even for that is very simple there is optimizations which we are getting, if we are spending too much of time on optimization, then it is not there is advantageous. So, try to spend some amount of time and some amount of effort, but you try to find out what is going to be the outcome. So, if the outcome is like we have a very huge amount of there is improvement in the timing, and we have very huge amount of that is saving in your space, then we can find it is going to be really useful to go for the optimization. At the same time, you should not spend too much of effort on your optimization also. So, that is about your the optimization requirements. So, now we shall see that is what is going to be the next phase. The next phase is the code generation phase. So, we find that is going to be the last phase of your compilation, and this is your synthesis component. We have the front end and back end, but this is a back end component, or you can say that the analysis part as well as the synthesis part. So, in the case of analysis part, we include the first 3 phases, and the remaining phases are coming under the synthesis part. So, synthesis part is your code optimizer or even the code generation, they are all coming under the synthesis part. So, this is, as I told you earlier, this is the phase which takes the machine as an input, because the code is going to be generated for a machine, specific machine, and when you are generating code for the specific machine, the machine should be able to understand that. So, without the knowledge of the machine, you cannot go for the object code creation. So, what are the factors to be remembered when you are generating the object code? So, the first thing is, so we should know what is going to be the instruction format of the that is your resulting architecture, that is your target architecture for which we are generating the code. And the second one is, what are the various registers available in your that is your target architecture, so that we can generate that is instructions for specific registers, and the all the registers can be optimally used, especially with when you are having registers which are that is you are having 32-bit size, or it is going to be 16-bit size, then we can have the register combinations or register pairs, or specific registers which are dedicated for certain jobs. So, all those factors must be taken into account that is before generating the code. So, for example, if I am having a dedicated register for a stack pointer, if without bothering about that, if I go for allocating a general purpose register for handling a stack pointer, then it will be tedious. So, we need to have a lot of conditions regarding that. So, try to have the dedicated registers for the dedicated purposes, or the special purpose registers for the purposes for which they are intended. So, that is about the various things. We shall see that is what the other details we are having. So, it converts the intermediate code into the sequence of machine instructions. So, that is what being the job, because the input for any code generation phase is going to be the intermediate code, which may be the 3-address statement or syntax tree or even the postfix notation as specified by the compiler for compiler as the intermediate language. And the target language is going to be the machine code. If it is the case, then registers and memory locations are selected for each variable used by the program. So, that is another important job to be done by your code generation phase. So, if it is, we are very sure that the machine code is going to be the target language, then you generate that is your find out the registers for the various variables, and find out the memory to be assigned for the various variables, so which are going to be used by the program. And another important aspect is the code generation is judicious assignment of registers to hold the variables. So, the proper set of registers must be used for the that is variables which are there in your that is code. So, that is another important issue. So, storage allocation decisions which are made either during the intermediate code generation or during the code generation phase also. So, that is about the code generation. So, we specify what is going to be the intermediate language and specify what is going to be the target language, and if it is going to be the machine language, then we need to find out the appropriate registers and appropriate memory locations for the program. And another thing is the optimal pattern of your registers. So, we can even go for the reuse of registers, that is another issue. Reuse of memory locations, they all will be taken into care when you are generating the object code. So, with this we are having we have finished the various phases of the compilation. But the phase of compilation, when we learn with that, we must address two important things. One is the symbol table management, and another is going to be the error routines. So when you look at the symbol table, so it is what it is job. So it is going to be a data structure which has a record for each variable name with fields for the attributes and the name. So every variable in the program must be entered into a data structure in a record format, and the record includes what is the name of the variable and what is the type of variable, what are the other attributes like the size, what is going to be the scope. And if it is going to be a simple data type, this is okay, but it can be an array also. If it is going to be an array, so in that case we will be going for storing the number of dimensions and the size of each dimension and etc. When it is going to be a record, what are all the fields available in the inside the record and what are their types. So these are the things which we have to store along with the symbol names into the symbol table. So the another very important requirement here is, so most of the time we will find your symbol table is being searched. So once we go for installing a symbol table into the table, but we will go for many times the searching operation. The searching operation is supposed to be done in a very faster manner, so that the compiler will compile the code in a efficient way. So if the data structure has no support for faster execution or faster searching, then that itself is a bottleneck in the compilation process. So the data structure which we are selecting, it should be it should allow the compiler to find the record for some name, that is for each name quickly, and to store or retrieve the data from that record quickly. And the compiler is supposed to record the variable names used in the source program and collect information about various attributes for each name. So these attributes provide the information about like storage allocated for the name, its type and its scope, etc. So in the case of procedures, so what will be done is the procedure name is a very important factor, and then we have to that is say what is going to be the number of arguments being passed for the procedure, and what are their types, and what is going to be the method of passing, that is each argument. It can be either a call by value or call by reference or call by name, or so these are the various types of parameter passing methods. And another thing is the scope. The scopes must be implemented by setting separate symbol table for each scope. So that is one issue. So one way of handling the scope, but it is not required that we must always handle the that is scopes by separate symbol table, but you can include another, that is field, saying that what is the block within which it is having the declaration. So normally the program blocks with the declarations will have its own symbol table for each entry, with an entry for each declaration in the block. A class is having its own table with an entry for each field and its method. And the symbol table entries are created by the parser, that is a lexical analyzer and the parser, and even the semantic analyzer, but remaining phases they will be using the symbol table as a tool for just lookup and all. So that is about the that is the symbol table management. And so symbol table is a very important component of your program compilation. Without the symbol table, it is very difficult to manage with the code generation and all. And the symbol table must be designed with an intention that it should be very faster in terms of accessing, because most of the time we will go for search operation as far as symbol tables are concerned. So it must be much faster in satisfying the various search operations. So to summarize, we have seen the intermediate code generation, which is simplifying the source program, and then we are making use of the code optimizer to find the that is your optimized code. And then we have seen that is code generator, which translate the object program version translate the high level language program into its equivalent object version. And then symbol table manages the various names and their scopes. Also there is a concept called the number of passes, how it is affecting the program and design of compilers. So more the passes, the compiler design will be much easier, but less number of passes, the compiler design will be very complicated. But more the passes, the compilation will take much amount of time. Less the number of passes, the compiler takes less amount of that is time, because of the intermediate file representation. So the questions, the familiar intermediate languages. So what are the role of the code optimizer? What are the important factors to be remembered while generating the object code, and the pros and cons of increasing or decreasing the number of passes. So that is about your various phases of compilation. So with this I conclude this episode. Thank you all.